I just want to say welcome, everybody. We are really glad to have you here with us today. My name is Stephanie Suber. I am the Director of Outreach and Communications at RENCI. I will be your moderator today as we walk through a conversation with a few of my colleagues about their pieces of RENCI that have occurred over time. If you want to hop over to the next slide. We're going to do a little bit of housekeeping items. So the first thing I want you all to know is that we have disabled the Zoom Q&A and the chat for attendees. So if you try to type something to us, it won't work. That is to be expected. We want to allow our speakers to present without distraction. But we do want your engagement. We want lots of engagement and questions for after the presentations are done. We hope to have a robust conversation. And what we have set up to do that is an easy retro. And so you can put your questions, your comments there. It's a crowdsourcing Q&A platform that just makes things a little easier to follow, I think. And so I think Jayshree has dropped the link to the easy retro in the Zoom chat. Instructions are here. They're covered in this slide. It's a pretty intuitive interface. A little plus sign lets you add your question, and then as questions are added, you can thumbs up things and say, yeah, that's a really good question. I hope that they ask that one. And you can also, of course, add your own questions. And we'll share this slide again at the end of the Q&A period, but we do invite you to add questions as presenters are sharing. We'll sort of like periodically drop it into the chat for new folks that might come on. And so that's what we have set up for how to engage with our webinar today. And so if you want to move on to the next slide, this is why we're here, talk a little bit about RENCI. So for those of you who might be unfamiliar with RENCI, this first slide showcases a bit of who we are. And so there's a lot going on. We'll start at the bottom of the slide. So if you view from the bottom up, the first row at the bottom is included because we are a research institute at UNC Chapel Hill. We were launched in 2004 in collaboration with Duke and NC State. So hence that bottom layer. If you move up from that row, you can see the gray semicircle that highlights our core methodologies that we use to enable research, innovation, and economic development. So you've got the data science, computing, networking, software and visualization, in that particular section. And then we go out further to see that we use those methodologies to engage with universities, industry, and also government partners. And then, of course, at the very top, we are capturing that all of that work that we do is done in multiple scientific domains. So that's kind of RENCI at a glance. If you'll go to the next slide, this slide is here because I know that the last slide was a lot. Maybe people will view it in the recording and, really just soak into it. But this slide kind of captures like, okay, RENCI does a lot, but if there's one thing that I'd say for you to remember about RENCI today, it's captured here. And it's that we believe in interdisciplinary collaboration, building communities, and innovative technology, and that we understand that at the core of all of those things are people. And so the essence of what we do every day is we work with others, creating and improving innovative technologies that advance science to benefit people. So don't forget that. So with the next slide, we'll move into 3 specific examples of the type of work we're involved in that we hope stays close to those ideals that I just articulated for you. Obviously, these are not the only examples of things that are happening at RENCI, but they're really important ones that I think showcase how we've evolved over 20 years, right? We're here to celebrate 20 years of innovation. We were launched in 2004, and I think each of these particular specific examples show like a trajectory over time. And so with that said, I will go ahead and introduce our first speaker. One moment. I'm gonna give a huge shout out here to our amazing security experts at RENCI who make sure that we are very secure, but also that I just had to log into my notes. So Thanks. But I will introduce Anirban now. So Dr. Anirban Mandal is gonna share his screen or his video. He is our director for the Network Research and Infrastructure Group at RENCI. He is a computer systems researcher with a primary focus in research at the intersection of distributed systems and scientific computing. And at RENCI, he leads several efforts in cyber infrastructure research in support of science. And his research interests lie in the areas of distributed systems, cloud computing, networking, and data-driven scientific workflows. So take it away, Anirban. Welcome.
Thank you, Steph, for the nice introduction. Jayasree, next slide, please. Yes. So our group at RENCI is Network Research and Infrastructure Group. In short, we say NRING. So primarily, we design, develop, deploy, and manage large-scale distributed cyber infrastructure systems and networks that support scientific research. And we have a dual focus in developing these large-scale infrastructures. The first focus is to do research on networking and distributed systems on top of the infrastructure that we develop. And then how do we research in the support for domain science applications that can utilize that advanced infrastructure to accelerate scientific discovery and innovations. So our group has been in existence for more than 15 years now. We started with 3 people, and now we are at 10 people. Most of our projects are funded through grants from the NSF and the Department of Energy, and our projects are collaborations across universities and research organizations and labs around the US and beyond. Next slide, please. So there are 4 primary focus areas for NRIG. Of course, we design and develop and deploy large-scale infrastructure. And on top of that, we do research on 2 aspects, right? We research on CI systems and networking, covering a variety of areas using distributed applications and workflows, next-generation networks, resource provisioning, cybersecurity, Internet of Things, and many other CI kind of areas. At the same time, we enable domain science applications and try to bridge the gap between those applications and how those applications can use these advanced infrastructures. And we do research toward that goal, right? So we advise on CI solutions for scientific facilities, customized research prototypes and solutions, and broadly help scientific applications leverage these advanced infrastructures. And then we bring all of them together by broadening the user base for our infrastructure that we develop. We do community building around our infrastructure and the different research areas, and then get to training the researchers and scientists on relevant CI topics. Next slide, please. So this is a scary slide, but this gives you an impression on the evolution of the research in our group, going all the way back to 2008, 2009, when we started. And this gives an overview of the different projects in those 4 thrust areas that I talked about. The projects at the bottom are our foundational infrastructure-related projects, and how those projects developed into research into different areas and supporting projects over time, research in CI systems and networking, research in scientific application support, and engagement outreach and training, right? So this gives you a flavor on how we build projects on top of previous existing projects, leveraging our successes and solutions, learning from our experience, applying our work to other research areas. Just next slide, please. Right. So as I said, our foundational research track is our work on managing large-scale, national-scale network infrastructure. And we had our beginnings in an NSF large-scale project called the GENI project. GENI stands for Global Environment for Network Innovations. It was, I think, a $120 million national program that reimagined building of the future internet and network research. Regionally, we built something called BEN, which is short form for Breakable Experimental Network. And there we did early experiments with programmable networks and software-defined networking using a local optical network testbed that spanned our campus, UNC, RENCI, NC State, and Duke. And this was an early example of how we built regional collaborations with RENCI and the regional universities, right? So we had our hands dirty by doing very involved research in this early focus areas for networking at that time. And we're kind of trailblazers in getting that kind of technology into a large scale project like NSF GENI project. And because of that, we got to design, deploy, and develop the ExoGenie testbed, which is one of the two GENI testbeds. And ExoGenie brought two innovations at that time together: innovation in open cloud computing using OpenStack, and innovation in dynamic network circuits. So ExoGenie was the project that deployed this large-scale network infrastructure across more than 30 campuses in the US, connected through layer 2 networks like Internet 2. And it was possible for experimenters to experiment with a variety of applications on this testbed. So with that experience, we gained reputation in the community to develop these large-scale network testbeds and large-scale CI. And so after about, say, 8 to 10 years of the ExoGenie project, we led an NSF mid-scale research infrastructure project called the Fabric project. And as you might be knowing, that the NSF mid-scale projects are one of the largest NSF investments in scientific facilities. It funds like instruments, NMR, spectrometers, laser instruments, and it envisioned network as an instrument of research. And RENCI and our group were responsible for designing and deploying and now managing the Fabric network testbed. At the same time, we're also involved in other large-scale NSF projects like the Chameleon Cloud project, which develops a cloud testbed for researchers. We're also involved in a wireless testbed. So you can see that we span a spectrum of infrastructure activities across this large time scale. And we are very happy to be involved in Fabric, Chameleon 4, and other projects. JC, next slide, please. So as I said, we developed other research projects with the infrastructure as a foundation. We did a lot of projects in networking research and development, SDNs with international research networks. We did a lot of work on cybersecurity research through NSF CI/CI funding, then cloud and IoT research, smart cities research. So this also shows the progression of those projects over time. Next slide, please. So the other important aspect was, how can science applications leverage these kinds of infrastructures? So we had a series of projects funded both by DOE at the bottom here and by the NSF CC STAR grants and other SDCI grants that took care of this bridging the gap between infrastructure and applications. And then we have projects like CI Campus, which provides expertise to NSF major facilities. So we not only develop systems and do research on them, we're also seen as a group that can evangelize that work to the broader community. Next slide, please. So this gives an example of two NRIC projects. I already talked about Fabric. There's an URL here. Please go and take a look at this project. And the other project is the CI Compass project. I would encourage everyone to contact RENCI and me to get more information on that. Next slide, please. Yeah, so this gives a flavor of the coverage of the different projects across the 4 thrust areas. And the next slide shows the different collaborative institutions for our NRIC projects. Next slide, please. In terms of opportunities for collaboration, as I said, to do large-scale experimentation on a variety of research topics, please go to the Fabric website. If you want to scale up your applications to national scale, utilizing other federally funded resources, we can help the campus researchers and scientists leverage Access, Path, and other NSF facilities. We can help with potential applications in the edge to cloud continuum, drone applications, UAV applications, supporting AI applications. And last but not the least, we could also help in collaborating on privacy-preserving data infrastructure and computations, leveraging a plethora of health data sets at UNC. Thank you.
Thanks, Anirban. We appreciate that. I am always amazed by the breadth that is just like within your particular group at RENCI. So I appreciate that. So our next speaker is going to be Dr. Ashok Krishnamurthy. So he is the director of the Renaissance Computing Institute, or RENCI. He is a research professor of computer science at UNC Chapel Hill. He's also the co-director for informatics and data science at NC Trax. Ashok has many years of experience with informatics and data science, including data science cyber infrastructure, medical image analysis, time series data analysis, machine learning, and high performance computing. And he is also, as I said, our fearless leader. So welcome, Ashok.
Thank you, Stephanie, and thank you, Anirban, for that wonderful discussion of everything that that Enric does. Next slide, please. So what I was going to talk about was another particular slice of RENCI and how this particular slice of work that we do grew out of an early project that we took on. So, I'm going to be talking about these 4 different cyber infrastructure projects, which are all around data sharing and being able to work on these biomedical data sets, all for the National Institutes of Health. All of these projects actually had their start when Stein Ahold was the director at RENCI. He's now with the School of Data Science and Society. So I'm going to be talking a little bit about how the first one, the Data Commons pilot, ultimately led to these other 3 projects which are still in the works. Next slide, please. So what is the basic idea or principle that all of these projects embody at some level? And that is that, the cloud, the compute cloud is a very good method to enable data sharing. And just to give you a bit of data that isn't on here, I was talking to somebody at NIH leadership level, and one of the things they said was that in their estimate, there are certain very large data sets that are NIH proprietary data sets, but that are typically used by downloading to local institutions. And they estimated that this very large data set, there's probably about 60 copies of it existing across various infrastructure at different universities, because everybody downloads it and uses it, right? So right there, you see there's a vast amount of duplication, and anytime you duplicate data, things can go out of sync, etc. So the idea behind that NIH has been pursuing for a while is that data stays in the cloud, and then you do your work in the cloud, and that the data is curated and maintained in the cloud. It has many advantages. It levels the playing field for researchers at all institutions. You can access the data without having to physically copy it, etc. So the idea is captured in the graphic on the right, The old model was people download the data and then compute on it. The model that we are trying to bring into being, and RENCI is playing a role in this, is that the data stays in the cloud, and researchers log into workspaces in the cloud to work on the data. Next slide, please. So let's start off with the first one that kicked all this off. At least for RENCI, it was Data Commons pilot phase. This was supposed to be a data commons or a data workspace for across NIH, and it helped us to lead to what comes next. But as a common NIH workspace and data repository, it lasted for a couple of years, but never really came to fruition. Next slide, please. So this was the concept behind the Data Commons pilot. Like I said, it lasted just over a year. There were multiple institutions that were involved in trying to stand this up. The idea was that this would be a cloud agnostic platform. It would provide access to scalable and computable, and secure workspace environments and collaboration environments. Data, etc., would be available, right? And so the concept and the early beginnings, RENCI was involved in standing up as part of this a particular data workspace that we called Helium. We were called Team Helium, and we stood up a workspace for that. Next slide, please. As I said, the data commons effort in and of itself ended, but what it led to were that many of the NIH took what they could from the data commons effort and started launching their own. And our big partner, and that we have been working on for a while, is National Heart, Lung and Blood Institute, and the particular data commons is called the Biodata Catalyst, right? And again, the basic role is to be able to leverage all the cloud infrastructure platforms. Start with genomics as the fundamental data type, and expand to clinical data, and now imaging data and various other kinds of data. Make sure that the consent of the study participants and their privacy is preserved, and support advanced analytics and team science. And nowadays, as you can imagine, there's a big push to support AI on these platforms. What is RENCI's role in this? And again, in all of these data commons that I'm going to talk about, I'm only going to talk about RENCI and RENCI's role. But please understand that each of these data commons involves many other national partners working together, and each national partner has their own particular speciality and functionality that they bring to the table. I'm just not talking about that in the interest of time. Right? So RENCI is a coordinating center for the Biodata Catalyst. We are the ones who, at this point in time, working with NHLBI, develop the vision and help to move the platform forward. We make sure that we are actively engaged in growing the community, and as well as user training, etc. So that's our role in the Biodata Catalyst. Next slide, please. So if you want to understand what the Biodata Catalyst actually looks like, this particular chart kind of explains it succinctly in one figure. So on the left side, you see various data sources. So to begin with, genomics, clinical data, imaging data. These data sets are produced by a variety of studies by various researchers. These data sets are then ingested into the Biodata Catalyst, where they become searchable and analyzable. And so the Biodata Catalyst in the cloud, through a number of our partners and partner platforms, provide workflows, provide tools that you can use to do analysis. As I said, now we are growing more and more AI analysis. and all with the idea of being able to make new discoveries that can lead to new diagnostic tools or new therapies or new prevention strategies, with the ultimate goal that it benefits patients. Next slide, please. So much of the biodata catalyst is, as I said, ingesting many data sets. One of the big ones that we are supporting is the TopMed data set, which, as the slide explains, has whole genome sequencing and other kinds of patient data that we are ingesting. Next slide, please. Quickly talk about the HEAL initiative, which is around opioid addiction and pain medication. The difference between the HEAL approach and the biodata catalyst approach is that the data in the HEAL approach is distributed. It resides at various repositories, and RENCI's role is to help the researchers decide how to put it in the various repositories and then be able to access it to do the analysis. Next slide, please. This gives you a picture of how the HEAL ecosystem works. There are different studies that go into various repositories, and then they are moved to an analysis platform to do the analysis. So as opposed to all the data being in one place, they're still in the cloud, but kind of distributed. Next slide, please. This again tells you the three major components of HEAL: the HEAL connections, HEAL stewards, and the HEAL data platform itself. RENCI leads the HEAL stewards effort in this. Next slide, please. Finally, I want to talk about the last one. I think I may be out. Am I out of time, Steph, or can I quickly talk? Okay. So the RADx Data Hub is basically around data related to COVID-19 testing data that has been collected at a number of different institutions. And this again goes back to a centralized data approach. All the data lives in one data commons with workspace tools that users can log in and use. Next slide, please. So you can see there are 4 major studies that have contributed data to the RADx Data Hub: RADx Up, RADx Tech, RADx Rad, and the digital health technologies. RENCI's role is in coordinating how these repository is built, as well as being able to do user outreach and support users on the platform. Next slide, please. So here is information about each of the 3 platforms I talked about: the Biodata Catalyst, the HEAL, and RADx Data Hub. If you're interested in working on any of these, you can get hold of us, and here are links to learn more about them. Next slide, please. Okay,
Thanks,
that
Ashok.
was it, and I think I ran out of time also.
Yep, you ran it perfectly. So we are on schedule. So much appreciation for that talk. And I will introduce you all to our next speaker. Dr. Chris Bizon is the Director of Analytics and Data Science Group at RENCI. He leads a team that applies a range of analytical methods, including knowledge graphs, machine learning, visual analytics, semantic web-based reasoning, and textual annotation across many different domains. So welcome, Chris.
Thanks, Steph. And thank you, everyone, for your time this morning. So as Stephanie just said, the Analytics and Data Science Group, our remit, as I see it, is largely to engage with people from all sorts of domains who have questions that can be pushed forward by applying some sort of analytics or interesting computer science or data science approaches to solving them. And so our group is largely agnostic on domain, although we have a fairly large concentration in health and biomedical research. We also have projects in transportation and in art history, and sort of all over the place. And we apply a range of different analytical methods and tools, whatever might be appropriate to that particular question. So today, I'm going to focus on one of the columns on this slide, which will be the work that we've done around knowledge graphs. So next slide, please. So what am I talking about? Well, in some ways, a knowledge graph is just a database. And, that maybe is a dirty secret, but there it is. And that's not very exciting in some sense. But if you start to think about why it might be exciting, it's a particular kind of way of structuring information. I mean, that's what a database is in some sense. And in this case, what I mean is that you have your information structured like this. You have things, which are these blobs on the screen, which are called nodes, and they represent something, usually something in the real world, maybe a chemical or a process. And then you have relationships between them, which are these green edges. So you might say, oh, this gene DDHD1 is actively involved in lipid catabolic process, right? That's a relationship. It's a statement that somebody can understand, and it's structured it's in a certain way that makes it computational, right? You can do computational work on it, but it's understandable to someone in a domain who can read that statement and say, oh, I see what you're saying. And so when you string a bunch of these kinds of relationships together, they make this sort of graph structure. Next slide, please. So in some sense, so what, or what can you do with it, or how do you make one, right? So those are a set of questions. This is about a particular project that we have called RoboCop. And what we do in RoboCop is construct knowledge graphs by ingesting curated sources. The thing about curated sources is there's a lot of them. So a lot of people spend a lot of time making different sorts of data sets that they make available. The interesting thing is, even though these data sets are often in a structured form and they've been curated by a person, they're not usually very interoperable. It's very hard to get them to work together because people use a different data model or they use a different set of identifiers. So even though they're talking about the same gene, for instance, you can't recognize it as the same gene unless you happen to know that, gene NCBI 47 is the same as HGNC 36, right? And so what we do in the RoboCop project is we consume these different curated knowledge sources. We put them through a harmonization process that conforms them to the same data model and a standard set of identifiers. That's happening in that box labeled Orion there. And then those, we make those now interoperable sets of graphs available. So those have all been turned into interoperable knowledge graphs at that point. Then we also merge them all into one big graph that we call RoboCop KG and make all of that available for querying at the website that you can see there. So there's different ways you can talk to it. You can send API queries, but you can also use this kind of graphical query interface to find out the answers to questions. As the project continues, I think we have another 3 years here. We'll be building a variety of tools on top of this graph to enable researchers to answer more and more questions. Next slide, please. Going down a similar road, we've been involved in a project called the NCATS Biomedical Data Translator for a number of years. And the idea here is we're going to consume, there are many groups that are doing what we're doing in RoboCop, that are consuming these knowledge sources and making graphs. And what we're doing in Translator is integrating those at even a higher level. So we can see here we have many different knowledge sources. They all get converted into a common format again and allow users to ask questions of the data. In this case, the questions can be not just direct lookups into a database, but actually there are inference type questions happening here. So if you say, for instance, what chemical might treat diabetes, you're not just asking, oh, tell me about metformin. You're asking, find me new chemicals that I don't already know about that might be a novel treatment for diabetes, and explain why. And the idea is that because you have all of this structured information, you can sort of find paths through that graph that allow you to make a new inference. The site there, the ui.translator.io, is the user interface that people can use to ask these types of questions and get answers back, along with all of the supporting information coming from the knowledge graphs. Next slide, please. So continuing down that road, there are many ways to perform inference on these graphs. What does inference really mean in a graph? Well, if you have a graph and it's a set of nodes that are related by edges, the idea is to find and infer new edges in the graph. So in other words, if I will have a node representing a chemical and I have another node representing a disease like, diabetes, if I can draw a new edge between that chemical and that diabetes node saying treats, then I've made an inference that that new chemical might treat diabetes. So that's the underlying idea behind this project. So this is a new project that we are engaged in. It's being led by a team at UPenn and the Every Cure nonprofit. And the idea is to do large-scale drug repurposing. So in drug repurposing, the idea is frequently that I've got a chemical and I want to extend its patent, say, by finding other things it might treat. Or I have a particular disease I'm interested in, and I want to find chemicals that might treat that disease. The idea of Every Cure is to say, we don't really care what disease we treat. We don't really care what chemical we use to treat it. We're just going to perform inference of every chemical against every disease and choose the ones that are most likely to hit. And then we carry those forward through a set of clinical trials and so forth. But at the very front part of that, doing that inference, it's all based on the knowledge graphs that we and other teams are creating and the inference that we perform upon them. Next slide, please. Another thing you can do with the knowledge graphs is you can use it to aid search. So we have a tool at RENCI that uses that same RoboCop knowledge graph to perform what we call semantic search, where when a user puts in a term, you can go to the graph, find that node that they're looking for, and then look around in the graph in a structured way to find other information about that node and connect them with information that they might not be aware of if you're just using a basic text search. So this tool, Doug, is now underlying the semantic search at some of the on some of the platforms that Ashok was just talking about, namely on the HEAL platform and on RADx and on BDC. Next slide, please. So let me skip this one and move on to the next one. Thanks. One other fun project here is going back to how do you make these graphs. So as I told you before, we frequently make them by starting with already curated knowledge, but there's an awful lot of information in the scientific literature that is not yet curated into already structured information. And so there have frequently been attempts to extract new relationships from the scientific literature using natural language processing. As you know, natural language processing in the last couple of years has taken some pretty quantum leaps. And so the idea of this project, Litcoin, is to use large language models to extract new relationships to augment graphs, and specifically focusing on abstracts related to the HEAL project, the Helping End Addiction Long Term. So we have a set of tools based on LLMs that can look at an abstract, extract the most novel findings, convert those into triples, and then transform those triples into the same sets of identifiers and models that we use in the other biomedical knowledge graphs, and then integrate that all together with the knowledge graphs that we already have, which can now provide context for these novel findings. Let's see, next slide. I think that might be it. Okay, right. So these are links to some of the tools that I talked about. So the RoboCop knowledge graph you can play with and query there, the NCATS data translator UI, and Node Normalizer is more of an API. But if you are somebody who is engaged in doing identifier munging, and if you are, then you'll know what I'm talking about, this can be a very useful API for you to send a query to and get back all of the other queries that that we can identify with it. And you can see my contact information there. Thanks.
Thank you, Chris. I'm always so interested in your work, especially around knowledge graphs and like what it can potentially do for people. And I give you extra credit for having an alpaca on your slide. So at this point, I'd like to invite Anirban and Ashok to also share your screens or your videos, and we will go into a roundtable discussion. Have just a few questions that we'll have a little conversation about, but I would use this time to remind you all who are attending that we do have the Easy Retro open. And so if you have questions that were sparked during the presentations or that are sparked as we kind of go through this discussion, we will take some questions from the audience for the last, 8 to 10 minutes or so. So feel free to engage on the Easy Retro at this point in time. So for the roundtable, I will just ask, basically a question of each of you, but I encourage you to like interact with each other if you have opinions on each other's questions. Anirban, the first one's for you. So I'm wondering, you talked about a lot of really amazing networking things that have been happening in your group for a long time that are happening now. How do you see advanced networking affecting research and science in the future for the better? Like, how are y'all changing the world?
Sure, I think that's a great question, Steph. I think fundamentally network research and scientific computing are related very closely in the sense that the outcomes of the networking research can help friction-free, high bandwidth, end-to-end data movement from the data sources on campus, instruments, laboratory equipments, distributed data stores, health data repositories, and researchers from that for those kinds of resources can come not only from the institutions themselves, but from other external institutions, partners, and collaborators, right? So the network research is very essential for affecting this high bandwidth, friction-free data transfers for the researchers so that they don't have to ship FedEx drives and so we want to make it easy to do the data movement, right? And sometimes the problem is at the last mile, right? How do you connect your instrument to the core of the campus network that goes outside, right? So a lot of the research is to develop this what we call as stitch ports that stitch the resources to the rest of the world, right? The other aspect I think which is important going forward is continuum computing, right? So where computing doesn't happen only at the cloud or HPC centers, it happens at the campuses, but it also happens at the edge resources on devices and in the network themselves, right? So how do you bring all that together by connecting those different forms of computing through networking research? And the third point I would say is with the advent of AI and federated learning, how do you do distributed computing effectively? And I think networking is at the center of enabling some of the methods for AI and federated learning. So I would cap it there. I'm sure there are many others, but I would let the panelists and roundtable researchers comment or ask questions on it, or the audience. Thank you.
Yeah. Ashok, Chris, do you want to add anything to that one?
The one thing, Chris, if you don't mind, the one thing I would say, Anirban, on one of your slides, you had this thing about, privacy preserving computation, etc. And again, from my experience working with health data, that can be a very, very powerful addition to the network-based work that you're doing, because in many cases, shipping data, shipping health data across different health systems is a major task. Takes years just to get the paperwork and permissions solved. Whereas if you can reliably allow distributed computing that exploits the network and ensures that the privacy and the protection is put all the way down in the application hierarchy, right? As opposed to being at the
Yeah.
surface level, but if it's embedded deep within the network itself, then that makes it much more harder to hack and perhaps much more reliably. So that I think that's that would be a great application going forward.
Yes, I agree. Yeah, thanks, Ashok, for the comment.
Great. So in the interest of time, I will hop over to a question for Chris, which I think you talked a little bit about kind of toward the end of what you were getting into. But AI is very central to the conversations that are happening right now in research. And so I wonder if you could say a little bit more about why you see knowledge graphs as important in the field of AI.
Sure. Yeah, I mean, that's a really good question. And I think there are a couple of ways that AI and knowledge graphs intersect, in my mind, at least. One is that, if you think about, I don't know, old AI or pre GPT type AI, a lot of it is sort of machine learning, and the idea usually is you're feeding some kind of structured information into this model, right? And it might be, a lot of times it's a spreadsheet type thing, right? You got a bunch of columns and you want to predict another column. Or it is images, some kind of regular sized thing that you can feed into this machine. And that's all well and good. And then we have a lot of data like that, and that's really useful. But there's a lot of data that is less structured than that, but still structured. So if you think about something like Wikidata or Wikipedia, not the text part, but kind of like the relationships, that's a very useful way to structure information. So you want to say Albert Einstein discovered the theory of relativity, things like that you can put into a structure, but it doesn't nicely fit into a table, right? It doesn't nicely fit into an image. And so it's an important way to structure information to feed into different types of modeling techniques. So there's that side. But a lot of times now when we talk about AI, of course, we're talking about text AI and generative AI of that type. And one thing that is very useful, as we all know, those tools know what they know, and they also know the things they don't know, right? That is, they are prone to giving you an answer, whether it's true or not. And what people often can do is use some type of structured information, frequently a knowledge graph, as a way to ground the large language model. So rather than let the large language model say whatever it wants, you use the knowledge graph as a kind of a memory for the large language model. So you have the large language model, someone asks a question, you can go into the graph and find facts, right, in a very structured, controlled way, which then you can present and say, okay, turn this back into text in a way that is helpful to the user.
Yeah, that was incredibly helpful to hear. I will say, panelists, if you have anything you want to add to that, feel free, and then we'll just jump into the last question before we go into general questions. So Ashok or Anirban, anything you want to add? I can tell Ashok's holding himself back. He's like, I want to talk about knowledge graphs and AI so much. Maybe we'll do a separate like lunch and learn webinar for everybody on that, because I think we could dive pretty deeply into that. But I will go into the next question. So for Ashok, so you did talk a little bit about this at the beginning of your call or your presentation, but maybe just a little bit deeper from the researcher perspective in particular about how working in the cloud can change or aid researchers in terms of like their workflow, reducing costs, advancing even further the work that they're doing by being in the cloud.
Yeah, thanks, Steph. I mean, I think that for a lot of researchers, it is a shift in how they are used to doing things, and so there needs to be a training or at least an ability to give them the resources that they need to understand how things happen differently in the cloud. One of the major worries that many researchers have when they work in the cloud is related to cost. That ultimately somebody has to pay for the cost of running something in the cloud, where you also pay when you're running on-prem on a local resource. But for the individual researcher, that cost is typically hidden. It becomes an institutional cost. Whereas when you're doing it in the cloud, it's very easy to assign it back to a particular project and a particular researcher. And so now it becomes the responsibility of each individual researcher to manage the cloud cost. So that is something that we need to figure out and we need to manage. On the other hand, it really allows them the ability to bring together multiple data sets much more easily, link across them, and also have very scalable computing. And ultimately, I think that once we figure out how to assign cloud costs, it can actually be a major advantage to the researchers, because then they don't have to worry about their own individual local resources.
Yep. Yeah, no more hard drives to be shipped places.
Right.
So we are going to open it up to questions from the chat now. And so please, you all feel free to continue upvoting on the Easy Retro or adding your own questions. So this first question is for Chris. How does Litcoin interact with potential reproducibility problems or trendiness bias in the literature? Is it degraded by these issues, which would be negative, or is it able to identify and mitigate or even address them, which would be positive? Any thoughts on that?
Yeah, I mean, that's a really good question. And I'd say it even goes a bit further than Litcoin. It's really for all of the knowledge graphs in general, because at the bottom, even if the information is being extracted by a person from the papers, right, and put into a structured form, which is the case in a lot of the curated data that we work with, that you still have that issue of reproducibility and trendiness. And so you'll often see something like there are, and this kind of ties into one of the other questions there about difficult problems. You'll often see that maybe one node is very heavily connected. And sometimes that's because, oh, that gene is just super important. But sometimes it's just, well, oh boy, that gene has been very heavily studied. And so the nice thing I think about Litcoin is that the long-term goal that the funder has in mind is that if we can figure out how to really do it, if we can get the technology right, then you can have a structured representation of every paper as part of the publication record. So what the funder is really thinking is somebody will write a paper, go to publish it. This technology will say, oh, I've taken your words and I've turned them into this nice structured representation. Is this what you meant, right? Is this something that would you agree with this representation of your paper? And that becomes part of the publication record. Mm-hmm. So now you at least have a computable way to engage with everything in the publication record. You can use that to devise algorithms to look for trendiness or to look for reproducibility or items that, this group said this and this group said that. Wait a minute, those don't line up, right? So that sort of thing should be aided by overall that long-term goal.
Great. Thank you. Thank you for that answer. So we have about 4 minutes left, so I'm just going to set the stage for everybody. I'm going to ask the two questions that have upvotes, and one is going to be a speed round between the three of you, so be prepared. But the very next one is for you, Ashok. So this question is, how do you think the work on data sharing and data ecosystems can translate into making UNC data assets fair?
Oh boy, that's a that's a big question. The best way, instead of going through and talking about all the different pieces that are involved, what I'll say is that between what Chris talked about as part of Litcoin, between what I sort of briefly touched on for Heal, as well as for Biodata Catalyst, if you take all of the tools and other methods that we have developed and are developing as part of these projects, those can form the foundation of how we can make UNC data fair. There's work involved. It's not that the tools immediately solve the problem for you, but we have the knowledge and the tools to be able to look across the breadth of UNC data and indeed be able to make them fair and usable and exploitable by other UNC researchers. So I'll stop there.
Well done. That was a meaty question and answered very succinctly and well, I think. So in the last couple of minutes before we close out, the other kind of upvoted question was, what is the biggest difference in RENCI scientifically from when you all started to now? So especially that you think might inform the kind of partnerships that RENCI can support. RENCI obviously started much smaller. We are larger now, both in people and I think maybe in the scale of work, as evidenced by what you all presented today. So I'll just randomly pick Anirban to go first to kind of give us his thoughts.
Yeah, sure. So I think from the as Steph said, in the past we were small, we had smaller projects, and we're trying to grow with collaborators from UNC and beyond. But I think the kind of projects that we have right now, I can talk from Enric's perspective, that Fabric is a national project, and we are being viewed as experts in this field, right? So we're being sought after by others. So we are much more responsible in terms of exploring what the community needs are in the future, and we're working more toward building a community for what would be the research focus thrust in the future, and try to shape our program going forward. So I'd say we're taking more leadership roles in larger scale projects, and that's only from Enric, but I'm sure in many of Chris's projects and many of the things that Ashok does also exemplifies RENCI's growth and forays into different areas.
Chris, do you want to weigh in really quickly?
Very quickly, although the question asks about differences, and there definitely are differences technologically and scientifically, I would actually emphasize the continuity of something, which I think is the curiosity of people at RENCI and the willingness to engage in a domain or learn a scientific discipline or a scientific technique that we know nothing about, but which we can use to aid in someone else's research.
Yeah, well phrased. Ashok?
It's
Last
extremely
call.
well put, both Chris and Anirban. The one thing I can add to what Anirban said, being able to manage and run very large projects, and what Chris said about a curiosity-driven, technically adept set of people who are willing to take on new challenges, very fundamental things to RENCI's success. I think that we are also being, by luck or just by action, being able to anticipate trends in where technology and where research tools need to go. And that has helped us both in terms of our shift to data science and now our shift to AI and machine learning and all those things. And that's hard to do, but if we can keep doing that, that'll be one of the major aspects of what RENCI is good at. So if you want to know where technology is heading, our track record is pretty good.
Well, that's a great note to end on. And thank you to those of you who stayed. I know we are just a couple of minutes over. Thank you to our presenters for such great and interesting information that you have shared today. And of course, to our audience for the great questions. If your question didn't get answered, or if you think of more questions, we have our contact us information in the chat. You can also always access us through our website, and we would love to collaborate and talk more with you. We will close things out now. An evaluation form of this webinar will pop up at the end, and we'd love for you to take a few moments to do that. But otherwise, I hope everybody has a wonderful afternoon.
Thank you.
care.
Thank you, Steph, Sujin, and Jayashree for putting together a wonderful program. I really appreciate it.
Thank you.
Thanks, everyone.
Thanks,
Take
everybody.
care, all. Bye.